recording has started. Good. Then I will share my window. Okay. Okay, so you see my window?
Hello, sir.
Hello? Do you see my window?
Sir, the name of book which you said.
Yes, sir.
Sir, the name of book you suggested, which should I buy, sir?
Actually, you can buy any good book, but you may.
Can you suggest one?
Maybe
Sir, I
this one.
told about Bala Guru Swami.
Yeah, Bala Guru Swami is good. It is good.
Okay, sir.
This is also fine. Okay, so do you see my screen?
Yes, sir.
Okay. So
Yes, sir.
let us start. Today's topic is about looping. So I will start loops and iterative programming. So from now onward, you will see that you can do some interesting things instead of just writing a sequence of statements, some conditional perhaps. Anyway, so before giving you a boring list of syntaxes, let me start with an example. Okay. Maybe you have heard about this, but let me introduce this. So consider positive integers. Some of these positive integers, these are also often called natural numbers. Okay. So you start with a number like 2021. Replace this number by the sum of the squares of these digits. So this is 2 square plus 0 square plus 2 square plus 1 square. So that is how much? 4 plus 4, 8 plus 1, 9. Then you replace this by the sum of the digit square. In this case, there is only one digit, so it's 9 square, that is 81. You keep on doing this. Okay, so 8 square plus 1 square. What is that? 65. From this, again, you replace this by 6 square plus 5 square. How much is that? 36 plus 25, 61, right? I think so. Then replace this by once again by 6 square plus 1 square, which is 37. And so on. This process is clear, right? You start with a positive integer, look at its decimal digits, take the squares of the individual digits, add them up. Replace that number by that sum. So the question is it possible that this will eventually come to 1? Okay, so that is the question. So after a finite number of repetitions of this, will this come to 1? Okay, so in general, let us say n, this you replace by sum of digit square n. This you replace by sum of digit square of sum of digit square of n, and so on. And eventually we ask the question, after some number of replacing of n by its sum of digit square, will it reach 1? You can see that once you reach 1, then if you do this thing, replace 1 by the sum of square, it will stay at 1. Okay. So if this happens, so if n in some number of iterations reduces to 1, we call n a happy number. And if after any number of iterations never reaches 1, n is called an unhappy or sad number. Okay. So in order to verify whether 2021 is happy or not, we can keep on doing these manual calculations, right? But let us write a program to find out whether 2021 is a lucky number, a happy number or not. Okay. Now the question is, how can a number be unhappy? The reason is that, let us see. You start from a number, let's say n1, replace it to n2, then n3, and so on, keep on doing this. Now, if eventually, let's say ni, and by a sequence of this transformation, if there are some I and j such that ni equals nj, then what will happen? This will simply keep on looping here. ni plus 1, ni plus 2, ni plus 3, blah, blah, blah. Nj is again equal to ni. So again, you will keep on traversing this loop. Okay. And if 1 does not belong to this loop, then there is no chance that starting from n1, you will eventually end up in 1. Is that clear? Okay.
Yes, sir.
Okay.
Yes, sir.
One possibility is n1 after some number of iterations eventually reduces to 1, and then of course it loops, but loops at 1. And otherwise, or n maybe. Another situation is that this goes to something ni, then after a big loop, possibly big loop, it will simply keep on traversing this loop, and 1 does not belong to this loop. Okay, so let us write a program to verify whether any number like 2021 is happy or not. Okay, first let me be a little bit naive. So vi, let's say happy.c. So as usual, I will have these two lines, stdio.h and stdlib.h. Then in our main function, I will declare several variables. N is the input number. I will keep a copy of n because I will replace n by the sum of digit square of n. Okay. So actually I require 2 copies. So we will see. These are called m. And also I need some sum. Okay. So that's all I actually require. Somebody is okay. So first I ask the user to enter n. So I just leave a prompt. Enter n. And then you read and n. And you may actually, this is integer, positive integer. So if n is, you can just make it positive. N is less than 0, just replace it by minus n. So now n becomes a positive integer. Or if you have unsigned integer, then this step is not necessary. Anyway, so this is the input part. Okay. Okay. So then what I will do? Yes, this is a mistake. Okay. So for the moment, I will keep a copy of n to capital N, because at the end, I will print this capital N, original input of the user. Okay. Okay. So this is what my loop is. So I start from a new line maybe. While n is not reduced to 1, you repeat this part. Okay. What do you do? I will replace n by the sum of the digits. So I have to, given a thing like this 2021, I have to extract the digits. That can be done by repeatedly dividing by 10. Okay. So divide by 10, you will get this digit 1 if you take remainder. And if you take quotient, so 1 is considered, replace n by 10. So this 202 will remain. Keep on doing this until this number reduces to 0. Okay. So what I will do, I will keep another copy of n. And I will say, as long as m is not reduced to 0. Okay, so I need a little bit more initialization. Sum is 0. Okay, maybe let me use another variable for clear understanding. M is not 0, so you divide m by 10. This is taking remainder. And replace m by 10. So you could also use m slash equal to 10, short circuit operator. So this is quotient. Okay. And so you have extracted this digit d and discarded that digit d from m. Okay. Then what you will do, add to sum, this time I do it this way, the square of t. So is this chunk clear? This inside the body of the loop? As long as m is not reduced to 0, consider the next or the least significant decimal digit, and then you discard that digit from m. And you have initialized this sum to 0. Add d square, the square of the digit, to this sum.
So, the while n not equal to 1, why is that condition there?
I will come to that. I will come to that. So in the variable s, you have computed this sum. Okay. Then you want to replace this original n by this sum. Right. So after I have computed this s, I will replace n by this sum. Okay. This is a little bit complicated example, but I deliberately start with a complicated example. Later I will give you the complete specification of the syntax of while loops, for loops, and do loops. Okay. So maybe what I do at this point, let me print the value of n, or here, maybe somewhere. The first n I anyway know. Okay, and maybe before just entering the loop, I will print the initial value of n. Okay. So I have kept a copy of this n, original n, in this capital N, because I need this value here for printing. Otherwise, I am replacing n by this sum, and the sum is computed by extracting the decimal digits from a copy of n one by one. Okay. And this sum accumulates the square of the digits, d square. So there is nothing called d square. So you should not use d caret 2. It has some other meaning in C. Okay. Anyway, so okay. So if ever n reduces to 1, then this loop will break. Okay, so this is continued as long as n is not equal to 1. If it reduces to 1, then this loop will be broken. And here I will then print %d is a happy number. What is that? I kept a copy because I have overwritten n by the sum of digits. So I just kept a copy of n in capital N and I print it here. And then, of course, you should have return 0 or exit 0. Okay. So if you do not understand every bit of this function, it's of this code, it's okay for the time being. I will one by one look at the exact syntaxes of while loops and other things. Okay. Let us now compile this. Good idea, warn all, happy.c. Okay, no compilation errors. Okay, so first let us give you an example. 13 maybe, a small thing. Or maybe just for a better presentation, I keep new line there. 30. So 1 square plus 3 square is 10. Then 1 square plus 0 square is 1. So 13 is a happy number. Okay. So what do you think about 2021?
Sad number.
Not a happy number.
Not a happy number. Let us see what happens.
Unhappy.
So this is basically an infinite loop. So I have to forcibly stop it. Okay. You see the cycle is something like 4 to 16, 16 to 37, 37 to 58, 58 to 89, then 145, 42, 20, and once again back to 4. Okay. The problem with this program is that there is no way with this simple-minded loop to capture unhappy numbers. If we supply as n a happy number, then this loop is broken. Eventually n reaches 1, this is broken, and it reads here, and it comes here. Okay. So the question is, how do I detect this kind of looping? Okay, so there are many sophisticated ways of doing it, but I will go by a little bit of mathematics. Okay, you look at this loop, 4, 16, 37, 58, 4 square is 16, 1 square plus 6 square is 37, 3 square plus 7 square is 9 plus 49, 58, 5 square plus 8 square is 25 plus 64, 89. Eventually you will come at 4 square plus 2 square, 24. And if you look at these computations, you see that I have already reached 37 here. Okay. So after that, what will happen? 37 will go to 58, then 89, then 145, 42, 24, 16, 37 again. So this will keep on repeating. So this is a big bad loop. Okay, so I want to find out whether it is looping. And if I find a looping behavior, I should also come out and say this is an unhappy number. Okay, so one possibility is I stored all the integers generated in this sequence. And whenever I generate the next value of next candidate for n, I will look at that entire storage. And if a match is found, I will break. This is a possibility. Fortunately, in this example, mathematics is going to help to simplify this code. It turns out that if n is a happy number, this will eventually reach 1 and then actually it will loop. And if n is an unhappy number, the only way it can become unhappy is by going to the loop containing 4. It is precisely this loop, 4, 16, 37, 58, 89, 145, 42, 20, back to 4. Okay, and if you look at this example, 61 is not part of the loop. The loop started from 37, but it will eventually go to 4. Okay. So the happy number ending is in 1 and then looping at 1 itself. For an unhappy or sad number, it will eventually reach 4 and then loop in this sequence 4, 16, 37, blah, blah, blah. Okay, why? So this is basically a mathematical question. So every unhappy number reduces to the loop containing 4. Why? This is a maths exercise. If you are interested, you can try to solve it using your mathematical skills. For example, you may use induction, strong induction. This is a possibility. Okay. So once I have this mathematical insight, I can now modify the code a little bit so that it can also detect unhappy numbers and terminate. Okay, while n is not equal to 1 and n is also not equal to 4, it will keep on repeating this task. Okay. Then the loop is broken as soon as n reaches 1 or n reaches 4. Okay. And then outside this loop, if n is 1, then you print this is a happy number. Okay.
So can you please explain a little bit about that, how it reaches 4 at the end for infinite?
This is actually a maths thing, maybe after the class. Okay. So if you are interested, I will explain you the proof. Little bit.
Sir, inside the while loop, shouldn't it be or?
If n is not equal to 1 or n is not equal to 4. No, why is it like that? This says that a happy number.
So if it is or, then if either of them is true, then like even if s becomes equal to 4, then also then also I think it would be true. Like
No, right. This is not equal to, not equal to. This is not equal to.
no, sir. I meant that if there is or, then if suppose s is equal to 4, then it should run for infinite time. But the second condition will be false. The first condition will be true. If it is odd, then it will still enter the loop.
Yeah, yeah. So and is the correct condition. So this in English it says that as long as n is not reduced to 1 and n is also not reduced to 4. Right. So in English, so long as n is not reduced to 1 and n is not reduced to 4. Okay, so maybe I just write it before the loop. Okay, so you repeat. Now outside, this is broken. This is an AND condition. This is broken if this fails or this fails, and this fails when n equals 1. This fails when n is equal to 4. Of course, these two cannot fail together because n cannot be equal to 1 and 4 simultaneously. Then you just check if n equal to 1, you just print this is a happy number. If it is not 1, you print this is an unhappy number. So with this modification, let us recompile and enter the value 2021. Okay, so you start with 2021. Let us verify. Then 9, 81, 65, 61, 9, 81, 65, 61, 37, 58, 18, and eventually it will go to 4. And at that point of time, the loop is broken and you know this is an unhappy number. What is the next happy year? Let us see one by one. Next year. No, it's also unhappy. Next to next year. Okay, so it also comes back to 4. 2024.
2020.
2020.
Check for 2020.
That is past. So 2024.
Yes.
Okay.
The unhappy number.
Let's try. We don't have to do it much longer. 2025 is also unhappy. Now 2026. This is a happy number because it reduced to 1. Yes, but the next happy year, don't say we have to wait for 5 more years for the college to reopen. Okay. 2026 will be happy for other reasons. For example, the dual degrees will get your degree, and for some think of some other things. Okay. Anyway, so this gives you a broad description of how loops work. Okay. So what I will do, I will slightly modify this loop. Okay. And
Excuse me, sir.
Yeah, tell.
You write condition if loop ends with 4. You can also write loops end with 16 because after 4, 16 will also come.
You look at this
many
cycle.
other numbers.
You look at this cycle. So any number on that cycle will be good enough for your loop termination. And it's not a very big loop involving 8, 9 numbers, something like that. Okay, but I will just show an alternative construct.
Sir,
Yeah, tell.
sir, can you give any leads on how to prove this? Like 4 will be contained in every loop of an unhappy number.
I will. After the class, I will tell you. Okay. Let us look at this programming thing, and then if you are interested, after the class, I will tell you. Okay. So I have used something called while 1. So 1 is a condition, 1 is a value which is non-zero. So this is basically an infinite loop. Agree or not? So this condition 1, which is a constant condition, this is always true. So this basically is going to be an infinite loop. But then my desire was not to have an infinite loop. So what I will do, here I just check inside the loop if it has reduced to 1. No, not else. Else, if n is equal to 4, then I know that this is an unhappy number. Okay, so there are several ways. Here I give an explicit break statement. If n has reduced to 1, print it is a happy number and break the loop. Otherwise, if n reduces to 4, then we know that this is an unhappy number and also break this. Otherwise, keep on continuing. Okay, let us see that this also works. 2026. Okay. 2021. Okay, so this gives you examples of syntaxes of while, while inside while. So this is called a nested loop. Okay, so this is called a nested loop. So continue until m, which is a copy of n, reduces to 0. Okay, and then this is what is called, this statement is actually quite interesting. Prepare for the next iteration. Okay, so each execution of the loop body is called an iteration of the loop. Okay, so these are some technical terms. Okay, so you're preparing for the next iteration, and also you are checking whether you have reached this terminal condition. So that way also you can explicitly break. Okay, so while 1, okay, so now this is no longer so long as n is not reduced to 1. This is not. This is basically now an infinite loop. Okay, so or I may say continue until explicitly broken. Okay, so these are the explicit break statements. Okay, so that's basically the syntax. 2, 3, 4, 5, 6. Let us see. So unhappy. 3, 4, 5, 6, 7. Unhappy. 4, 5, 6, 7, 8. Happy. Okay. So.
Sir, please check for 25.
What?
For 25.
25. Okay.
Thank you, sir.
Okay. Okay. So now I believe this is a slightly non-trivial problem solving. Okay, it's no longer printing things and assigning things here and there and playing with just assignment conditions and all that stuff. And we actually do not know how many iterations this will make. Okay, it may be 10 iterations, 3, 5 iterations, and I believe it can be made arbitrarily large. 50 iterations, so maybe. Okay.
Sir,
Yeah, tell.
sir, can we print that first number from where this loop started?
Okay, so you can, for example, if you print this thing n here and another n here, this will be duplicate print. That's the reason I avoided. Printed outside, and then after it is replaced by the new sum, I will print it. Okay, otherwise, there will be duplicate printing, right? Beginning of the loop you are printing, end of the loop you are printing, and then once again you go to the top of the loop and you print it again. Okay. So this is fine, right? I can now actually go to the syntax. Any questions? Okay. I don't have enough time, so the while loop goes like this. So while condition repeat the loop one. Okay. And once again, if the body consists of just a single statement, then these curly brackets or braces are not necessary. Okay. So for example, I can say I equal to 0 while I less than 10 print. Okay. Double statement. Plus I. Okay. So once again, you see that there is no semicolon here. If you do something like this, while I less than 10, I equal to 0, while I less than 10, semicolon plus I. This essentially means this is a single statement loop, and that statement is this null statement. And inside this null statement, the loop body, you are doing nothing essentially. This loop will break because you are starting from I equal to 0, and eventually you are incrementing I. At some point of time, I becomes 10, and then the loop is broken. But here, since this is the null statement, it has no effect on I whatsoever, and therefore this is an infinite. So be careful. You should not give a semicolon here. Okay, careful. This is another common mistake when you start programming at the beginning. Okay, so while condition holds, execute the loop body, come back. So it's something like this. Check whether condition is true or false. If it is true, if it is false, anyway the loop is broken. If it is false, if it is true, execute the loop body, which is called B, and once again go to the top of the loop. Okay, so long as this condition holds. And when the condition no longer holds, you come out and go to the next section. Okay, next step. Maybe I will give you yet another example, this time slightly easier. Oops. Where is it? Okay. Okay, so this is basically a GCD calculator. Okay. So let me explain this. You start with, I want to compute the GCD of A and B. Okay, and this is basically what is called the Euclidean GCD algorithm. So if B is equal to 0, I assume that A is greater than B or greater than equal to. Okay. If not, I can just swap A and B. Okay. So if B reduces to 0, then A stores the GCD of A and B. Okay. So I will keep on repeating this loop as long as B is greater than 0. What do? I divide 78 by 21 and take the remainder. Okay. That remainder, let us call it R. Okay, so that is our long GCD calculation procedure. So now we keep on going computing the GCD of the smaller number and the new remainder that you have created. So A and B are now replaced by B and R. Okay, so this is the Euclidean GCD algorithm. Okay, the Euclidean GCD is something like this. GCD of A and B. So I assume that A is greater than equal to B. This is equal to A if B is equal to 0. So I assume that A is greater than equal to B and B is greater than equal to 0. Otherwise, it is the GCD of B and A percent B. Otherwise. Okay. So this program captures this Euclidean GCD algorithm. Start with A and B. As long as B is not reduced to 0, compute the next remainder and then replace A by B and B by this remainder. Okay. So A becomes B and B becomes this new remainder. Okay. And this loop is broken when eventually B reduces to 0. At that point of time, A stores the GCD. So I come out of the loop and print the GCD. Okay, so let us see how it works. Okay, so this is somewhere in memory where I have 3 variables A, B, and R. We assume that these are all integer variables. And before this, possibly A, B, R are all uninitialized. Okay, so you initialize A with 75. So 78 now will be stored here. Okay. Then you come to B equal to 21. So 21 value, this 21 will go here. Initializing B to 21. Now you check whether 21 is greater than 0. Checking if the value stored here is 21. This is greater than 0. Yes, it is true. So you enter the loop. Make an iteration of the loop. Okay, because this condition is now true. Okay, let's see what happens. Condition is true. So you enter the loop. So you compute the remainder A percent B. So now it is 78 percent 21, 63 plus 15. 15. Okay, so 15 will be computed and written here. Okay, 15 is computed. Then what you do, you move this value to A and this value to B. Okay. So A becomes B, so 21 will come here and 15 will come here in this statement. Okay. So 21 comes here. Of course, movement does not mean there is a void here. Okay, this will continue to hold its older value. And then this 15 will come here. It's a case of copying. So this ends one iteration, the first iteration of this loop, with the variables A, B, and R storing the values 21, 15, and 15. Okay. So now, once again, you go to the top of the loop and check the condition whether B, whatever value is stored as B, is bigger than 0. It is the case. Still, this is the case. So I will once again enter the loop body. So condition is true. So once again, the loop is entered. So now you compute 21% 15. So this is the first statement. And that is nothing but 6. 15 plus 6. 6. Then this 15 will come here, 6 will come here. Okay. 15 will come here, 6 will come here. Okay. And then you have reached the end of the loop. Go back to the top. 6 is greater than 0. This is still true. So we once again enter the loop. Compute 15% 6, which is 12 plus 3, 3. Okay. Computing next remainder, which is 3. And then make a shift. This will go, this will become 6, this will become 3. Okay. This will become 6, B will become 3. And you come here and once again see that this is bigger than 0. 3 is greater than 0. So you once again, this is actually the last time I am entering the loop. Condition is true, entering the loop. 6% 3 is 0. 0 is computed. Then this will come here, 0 will come here. Okay, 3 will come here, 0 will come here. Now when you go to the top of the loop and you check that this condition that B greater than 0 is no longer valid. Okay, this is no longer true. So this time the loop will break and this will come out and print this value stored in A as the GCD. Okay, the condition is now false, so the loop is broken, or loop is exited. So you come here and print GCD equal to 3. Happy or not? This is how loops work. Any questions?
Sir,
Yeah.
means the syntax is clear, but could you explain how this method is the correct one that it will calculate GCD in all cases?
Correctness actually follows from this. Now don't tell me to prove the correctness of Euclidean GCD algorithm. Okay. Because what did you do in your earlier days? 63, 15. And bring it here. Actually, this is 3, it doesn't really matter, but anyway, 15, 6, 15, 12, 3, 6. What is that? 6. Now you have 0, so that is done. Okay, and this is the last thing that you got, so this is the GCD. This is how this is how you computed GCD, right? In your childhood days? Yes or no?
Yes, sir.
No.
Yes.
Okay, we did differently. I calculated all the prime factors and then.
Yeah,
That's another way, but factoring a number, particularly a large number, this is another way. Yeah, I understand, but this is actually very complicated, or I would say, time-consuming process, because there are no easy ways of factoring large integers apparently. Okay, but for computing GCD, we do not have to factor. Okay. So this is what is called the Euclidean GCD algorithm. Replace A and B by B and the remainder of the division of A by B. Now, why this is true number theoretically? Of course, there is a proof, but let us not worry too much about this. Let us have faith that the procedure taught in your school days works. And this program is essentially nothing but a translation of this procedure to a language which the computer can understand. Only this much you need to understand for the moment. Okay, you don't ask the question why Euclidean GCD algorithm is true. That can be proved.
Okay, sir.
Okay, can be proved, and it requires a little bit of number theory. It's not so easy. Okay, so this is just a translation of this procedure to.
Sir, if we
C
compare
sequence.
between two numbers, one of which is 0, like wouldn't the comparison be invalid? Like, why the factor for? Oh no, I got it.
Yeah, I didn't get your question, but like, if you have already solved your doubt, it's okay. Okay, so this is how loops work. maybe since we have a little bit of time, so I can give you another example of a loop. These are called for loops. Okay, so maybe I just introduce you. Whatever we have done so far can also be written using for loops. Although this was motivated by doing something like this, for I equal to 1, 2, 3 up to n, maybe you initialize sum to 0, sum I star I. Okay, so you read some value of n from the user, initialize sum to 0, and then for I equal to 1 to n, you add I square to s. Okay, so what will be the final value? It is the sum of the first n squares, 1 square plus 2 square plus blah 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 n square, and this turns out to be n plus 1 to n plus 1 over 6, right? So the for loops naturally occur in this context. So I can say something like this: for initialize I to 1, no, sum, of course, you can initialize here or here. Anyway, I do it here. Initialize sum to 0. For I equal to 1, and repeat so long as I is less than equal to n, and I have assumed that n is read here somewhere. The user enters. Okay. Then increment I, and in the loop body, this is a single statement, therefore I do not need the parenthesis, the curly brackets, I star I. Okay. So this is how this works. For do some initialization work. So I can initialize s equal to 0 here also. So in fact, I can write it this way. S is initialized to 0, comma, I is initialized to 1, semicolon. This loop will run as long as I is less than equal to n. And after this body is executed, I is incremented by 1. Of course, there is not a necessity of incrementing I by 1. You can have any other thing. I can be incremented by 2 or 3 or 4 or any other condition. Okay. So this is the general syntax of a for loop, but I will, and this is usually the case when the for loops are most widely used. But the idea is this: for, this is the general statement, initialization statement, okay, semicolon, condition, semicolon, next, okay, next, let's say next iteration, prepare for the next iteration. Then you have this body. So it's just a handy way of doing this. So if I want to write it as a while loop, it goes like this. Do this initialization here, while the condition C is true. Do this body B, and then you do N, and then go back to this loop. Okay. So it is important to note that for loops are precondition loops. So even before entering the for loop for the first time, you are checking whether this condition C is true. Do this initialization here, but before entering, even for the first iteration, you check whether this condition is true. If not, this loop will not be executed. Okay. And then this is the loop body. and you have some prepare for the next iteration part that you can write here. So this translates to this. This is exactly same as this. Okay. Conversely, if you are given some loop like this, as we have seen in this example, so this is a kind of initialization. So I can write it as a for loop for, let's say, capital N equal to N. Or okay, fine. This also you can do, or you can, yeah, you can do it. Okay, so maybe I'll just rewrite this. Okay, so let's see. I can also write it, although this is not a natural way of writing for loops. Okay, for this is an initialization step. This is just storing. Okay, and since this is an infinite loop, I can just write 1 as the continuation condition. And okay, maybe prepare for the next iteration statement is basically N equal to S. So instead of writing it there, I can write N equal to S here. Okay, but then here I should remove this and just print that sum instead of N. And I'm saying this breaking condition is exactly as before. For N equal to N, this is some kind of initialization. This is an infinite loop. That's why I have used this condition 1. It's always true. And prepare for the next iteration. I have N equal to S, but I could have written N equal to S here, and I have just kept this part blank, semicolon. Nothing there. Blank statement. That is also allowed. And let's see what happens. (2021). Okay. Okay. Okay, so you see that there is a second iteration and an extra iteration. So actually I have not yet set N equal to 1, so it's preferable that I use the value of S. If the newly computed sum is 1, then it's happy. If it is 4, because I have switched this N equal to S somewhere else, right? Okay, so now it will end at 4. Okay. Yeah. So that's how for loops work. Maybe I will stop with an example of for loops. Open PDS Shockwave Flash for loop. Which one? Yeah, this one. Okay. So it's essentially I want to compute 1 square plus 2 square up to 6 square, but this can be any n. Okay. So the sum is initialized to 0. It's basically the same program, like this. Okay. So as long as I is less than equal to 6, so this is the important thing. Initialize S to 0. Of course, you can move this portion from here to here, but then you separate by commas, no longer semicolons. Okay, semicolon will mean this block is over, this block will start. So if you want to put multiple initialization things here, then put commas. S equal to 0, comma, I equal to 1, semicolon. Okay, this is also allowed. Anyway, I have done it outside. So S is initialized to 0. Oh, sorry. S is initialized to 0. Then initialize I to 1. So this is the loop initialization. So I is initialized to 1. But note that you do not immediately go to the loop body. Every time you go to the loop body, you first check the condition. Then you enter the loop body. So this is a precondition loop. Okay. So you check whether 1 is less than equal to 6. I is less than equal to 6. I currently stores the value 1, so it is true. So now you enter the loop body. Condition is true. Entering loop body. So add 1 star 1. That is 1 to S. So S now becomes 1. Okay. Then this loop breaks. Okay. Not breaks, I would say loop ends. This body ends. So you once again go to the top of the loop, but top means before going to the top of the loop, you will do this part. Increment I by 1. Then you once again come here, check the condition, and once again enter the loop. Okay. So now you go here, increment I by 1. This becomes 2. Okay. Then again you go to check the condition. 2 is less than equal to 6. Yes, this is true. So you enter the loop body again. 2 square, that is 4, will be added to S. So this will now become 5. Then this. So the sequence is this, and then this. Okay. Increment I, it will become 3. Again, come here, check the condition. 3 less than equal to 6. This is true. So add a 9. 3 square, that is 9. This will now become 14. Then the loop is over. So we once again go to the increment part. Plus I. This will become 4. 4 is less than equal to 6. This is true. So add 4 square, that is 16. 16 to S. This will now become 30. Again, this increment thing. So this will become 5. Okay. So 5 less than equal to 6. This is still correct. So you enter. Add 25. This will become 55. Again, this increment part. I become 6. 6 less than equal to 6 is still true. So you enter the loop. Actually, this is you are entering for the last time. So you are 36 to S. This now becomes 81. Sorry, 91. Increment I, now this becomes 7. So 7 less than equal to 6 is no longer true. So now you will not enter the loop body, you will simply go out. Okay, condition is false, exiting the for loop. Done. Okay, so these are precondition loops. Before entering the loop body, you always check for the condition. There is another I would say, type of loop. Maybe we'll look at in the next class. These are called post condition. You always enter the loop body once and then you check. Anyway, this is fine. You may live perfectly with only precondition loops. But it is important to note that for is a precondition loop. Okay, so this is maybe just once again I write this. So what is the so you enter here, then you do not go to the body. Check here. If it is true, you come here. Then go here, come here. Again check. This is thing. Enter with initialization, then check, come here. Body, increment, check. So this is the loop. Okay. But before the first iteration, you check. For example, if I have I equal to 6, I equal to 7, and then I write for I, or sorry, maybe n equal to 7. For I equal to 0, I less than equal to n, plus I, semicolon, something. Okay, that something is not very, maybe s plus equal to, or whatever. So this loop will not be executed because for I equal to, okay, sorry. Okay. So no. This initialization is not correct. So n equal to, let's say, -1. So it initializes I to 0 and then checks whether 0 is less than equal to -1. This is not true, so this loop will not be executed. No iterations. Okay, so this is the thing you should keep in mind. Otherwise, it's like a for loop. And it's naturally applicable when you do things like this. For I equal to 1 to n doing something. Okay, like adding I squared to it. Yeah, so you have seen two types of loops, while loops, for loops, their syntaxes. And this example illustrates that you can have loops inside loops. Maybe we will look at another example in the next class. And we will also study do loops, which is a post-condition loop. And yeah, so maybe you now tell me whether you have any question. Oh, it's already 4:12, I see.
Excuse me, sir.
Yeah, tell.
So you said we can increment also greater than 1, increment by
Whatever.
1 more than.
This is a general statement. Okay. Yeah, this is a general statement. Just a general statement with the semicolon missing at the end. And if you want to put multiple statements here, separate them by commas, not by semicolons, because semicolon has a special meaning in the for syntax here. Okay, so you may have n1 equal to something, n2 equal to something, plus plus n3, yeah, lots of things you can do, but this is separate by comma, comma, comma. Okay. Also, you may have just a null statement here, because if you put n, if you move n from here to here, then you don't have to write anything here. It may be just I semicolon C semicolon. Any of these things may be a blank. Okay. Yeah. Yeah, any other question?
Sir, in the previous example, if we put a condition in S also, then when will the loop terminate?
No, I don't understand your question. If in the
previous example, we put a condition on S also, like if S is less than equal to 15.
You can do that. You can do that.
Then up to which the loop will terminate? After I is less than 6 or S is less than 15?
This is a condition, right? So this
Yes,
condition can be something like I less than equal to 6 and sum less than equal to 100. So whichever happens earlier will force the loop to break.
Okay, sir.
Okay, whichever happens earlier.
Sir,
Excuse me, sir.
sir,
Yeah, tell.
any of the I, C, and N can be blank.
Any of this can be blank. Okay, C cannot be blank. I think C can also be blank. I and N can be definitely blank. For semicolon, semicolon, then this might be an infinite loop.
But C should not be blank because there we have to give a condition, I guess.
Yeah, but if you give nothing, I will just
No,
verify.
sir, C can be blank. C can be blank, in my opinion.
In which case it will be an infinite loop. So you have to explicitly break it.
Okay. Okay.
Yeah, you have to explicitly break. You have not given any condition, so by default this will be implied as there is no condition. Keep on continuing.
Or internally we can also give
Sir, how to explicitly break it?
if we give
Yes,
a
in this.
condition that if I reaches here, we will break like that. If, I mean inside the loop.
Yeah, so inside that you can always give some explicit break statements like this, break. If something happens, then you break.
Yes, sir. If C reaches or I reaches 100, then we will break it or something like that.
Something like that. You can anyway do it inside.
Okay, sir.
Yeah.
Excuse me, sir.
Yeah, yeah.
Suppose I is from 1 to 100 and we want to move only over odd numbers, then how we will write the condition?
Okay. Do it something like this, only odd numbers. For I equal to 1, I less than equal to 100. Of course, you can write it something like this, I plus equal to 2, Okay. So instead of plus plus I or I plus plus, you just say I plus equal to 2. Okay. This is the way you can do it, or also you can write it this way, plus plus I, comma plus plus I. 2 increments. But do not use semicolon here, because semicolon has a special meaning in the for syntax. If you want multiple statements, separate them by commas. Okay.
Okay, sir.
So these are two ways of
It
doing
will cover all number up to 100.
up to 100. Yes. You can have any general statement here without the, final semicolon. Although more often than not, we typically use it in this fashion. For I equal to 0, I less than equal to this. I equal to 0, I less than equal to n, or I less than n plus plus I. So this is the most typical usage of for. Okay. But the syntax is general enough so that you can do a lot of other things. But I suggest that you should not write loops like this. Okay, so it's not UB till until. I suggest that whenever you have a situation like this, it is preferable that you use while loop. It's much more readable. Right, this is not very readable, right? Okay, so the earlier while loop was better. Okay. Yeah. Yeah. Official class is over. So if you have questions, let me know. And if you still want me to give you an idea why that unhappy thing ends in 4, I will just tell you.
Sir,
Yeah, tell.
so once I was writing a code and when I compiled it, it showed that there is a segmentation error. What does it mean?
It's a difficult thing for me to explain right now. But in these days, in your initial days, the most likely cause of segmentation error or segmentation fault is you forgot AND in your scanf. Okay, so just check that. There are other sources, but you just check that you have all these ANDs, ampersand, in your scanf.
Thank you, sir.
So can you give a slight hint about that ending with 4 that
Yeah,
program happened?
I can do it provided that nobody else has a programming question. I will just give you a hint. Yeah, why? Yeah, tell if you have any question about loops. Otherwise, I will just tell a little bit about it and then we'll stop.
So you will explain that about the why we got 4 there in that question.
Yeah. That's the last thing. This is not a programming question. That's why I kept it as a side remark. Okay, so let me start it. Okay. So there are 2 steps. Okay, so question is why unhappy numbers end in the loop containing 4. Okay. So maybe from 1, 2, 3 up to 100, you write a code and you check that the number is either happy, that is it reduces to 1, or unhappy and ends in that loop with 4. So this is the first step. So you make some exhaustive search, write a small code, it's not a very difficult issue. Then you show that if n is greater than 100, this implies sum of digits squared of n is less than n. Okay, this proof is not actually very difficult. You can do it. If it is greater than 100 or greater than equal to 100, this will always be less than n. So that means starting from n, when you replace by this, you get a smaller value. Okay. Again, you apply this procedure, you will get a smaller value, so long as n is greater than 100. But this cannot proceed indefinitely because you are decreasing these integers, okay, to something smaller, something smaller, something smaller. So at some point of time, it will have to come to a value below 100. Okay. And from 100, something below 100, we know it will either reduce to 1 or it will end up in the loop involving 4. So that's the proof. Happy? That's the proof idea. Yeah. So this I leave to you. Verify. So for n less than equal to 100, this is not necessary to. For example, if I take 99, 9 square plus 9 square is 162, which is bigger than n. But as soon as I reach 100 or bigger, this is a true statement. Okay, so you just verify this. Yeah. Yeah, any other queries?
Okay, sir. Got the idea. Well,
Okay. Yeah. Yeah, okay, so thanks for joining.
Thank you, sir.
Okay, so let's.
thank you, sir.
Okay, so let us
Thank
meet
you, sir.
again. The
Thank
next.
you, sir.
Okay, bye.
Thank you, sir.
Thank you.
Bye, sir.
Stop sharing. And I should also stop recording.